Here's video 2 of chapter 11. So we jump back to comparing these intermolecular forces. So if we are comparing the strength, what we first have to do is just identify what type of forces are present. So HF, we know automatically, they're all going to have London dispersion. So we can go ahead and label them as that. HF, is it polar? Yes, because it's two different atoms attached. So therefore it does have dipole-dipole. And it also has hydrogen directly attached to an F, O, or N, so it also has hydrogen bonding, all three. N2 and O2 are not polar, so they only have London dispersion. HCl is polar because it's two different atoms attached, but it's not a hydrogen bonding example. So we just have London dispersion and dipole-dipole. So if we wanted to order these, we automatically know that HF wins. It has the strongest because it has hydrogen bonding. Next will be HCl because it has dipole-dipole. Then you compare the ones that only have London dispersion. And the way we compare those is molar mass. So oxygen is 32 grams, nitrogen is only 28. So oxygen is greater than nitrogen. Similarly here, CF4, only London dispersion. He's not polar. CF3H has fluorine on 3 sides and hydrogen on the 4th. That means he is polar because he doesn't have the same surrounding atoms. So he has London dispersion and dipole. And then CH3OH has London dispersion, dipole, and hydrogen bond because it has that H directly attached to the O. So here you can automatically put hydrogen bond guy way up ahead. Next, the dipole-dipole guy. And then lastly, the weakest would be the one with only London dispersion. We can use these to predict melting and boiling points. So if you have greater intermolecular forces, that means your molecules like each other. So the more they like each other, the greater energy it's going to take to melt and boil them. So they're going to have higher melting and boiling points. Vapor pressure is the pressure exerted at the top of a liquid. So these molecules are pushing up with some exertion. That's called vapor pressure. So if you take liquids at a given temperature and you compare them, what you're going to notice is that the greater the intermolecular forces, so if this liquid has high intermolecular forces and they like each other a lot, that means they are going to exert very little vapor pressure. They're not going to push up very much because they don't want to escape. If they want to stay where they are, they're not trying to escape, which means they're going to exert very low vapor pressure. So here I show you the greater intermolecular forces, the lower the vapor pressure. This is going to affect how easily something evaporates because you've got atmospheric pressure pushing down and there's a battle between atmospheric pressure and vapor pressure. So if you have greater vapor pressure, you're going to overcome atmospheric pressure more quickly, which that plays into this thing called volatility. So volatility is how easily a liquid evaporates. If you are very volatile, that means you evaporate very quickly. Well, just think logically. If substances like each other a lot, are they going to stay or are they going to leave? If they have great intermolecular forces and they like each other, they are not going to evaporate, so they're not very volatile. However, if you have low intermolecular forces and they don't like each other very much, that means they have greater vapor pressure. They're pushing up with a greater exertion because they're happy to escape. They don't really like each other, so they want to escape. Therefore, they are more volatile. They evaporate very readily. Viscosity is the resistance of a liquid to flow. This one also should make some logical sense. If the molecules like each other and have high intermolecular forces, then that makes them very sticky, like syrup. And if they're very sticky, then they are very viscous. They move very slowly and they resist flowing because they want to stay right where they are. And then surface tension is kind of what we're already familiar with, but how the attraction between the molecules at the surface of a liquid. So if bugs can float on water, for example, that's because the water molecules like each other and they are creating a film at the top of the water. So the greater the intermolecular forces, the greater the attraction between the neighboring molecules and the greater the surface tension. So the bug won't fall through because the water molecules are very attracted to each other. Here's a review of some phase changes or the phase changes. So There's sublimation, which goes straight from solid to gas. Then there is vaporization, which is liquid to gas. And there's melting or fusion, which is solid to liquid. In that direction, do you notice they're all going solid, liquid to gas, all in that direction? Those are all endothermic, meaning they all require energy because you are disturbing molecules and you're pulling them apart. So you're having to overcome some intermolecular forces, some attraction. Whereas the opposite are all exothermic. So deposition is gas going straight to a solid. Condensation is gas going down to liquid, and freezing liquid down to solid. Those are exothermic processes, so energy is being released as the molecules come back closer together. So think about molecules as magnets. It always requires energy to pull magnets apart. It'll release energy to put them back together. So if we look at the energy changes during these phase changes, we have what's called heat of fusion and heat of vaporization. Heat of fusion is the energy required to melt a solid at its melting point. And it's written here as delta H of fusion is kilojoules per mole. We'll look at an example down here. And heat of vaporization is the energy required to boil a liquid at its boiling point. And it's heat of vaporization, kilojoules per mole. Generally speaking, heat of vaporization is much greater than heat of fusion because vaporization pulls molecules apart from liquid to gas, which is a much bigger change than fusion, which is just going from solid to liquid. Here an example is the enthalpy of fusion of ethanol is 5.02 kilojoules per mole, and its enthalpy of vaporization is 38.56 kilojoules per mole. So what that means is to melt a mole of ethanol, it requires 5.02 kilojoules for every mole. To boil it, it requires 38.56 kilojoules for every mole. So here we can use these as conversion factors. So it says how much energy does it require to melt 55 grams. So ethanol, I would have to give you this formula, C2H5OH. To melt it, I'm going to first go grams to moles using the periodic table. And then melting should make us think fusion. So enthalpy of fusion is what I need. And I know that for every mole of ethanol, it's going to require 5.02 kilojoules. So we can multiply the top, divide by the bottom, and we get 5.99 kilojoules here. To vaporize it, the energy, we would take grams to moles again. And then our heat of vaporization tells us that for every 1 mole, it would require 38.56 kilojoules of energy. So we multiply and we get 46 kilojoules. So it takes only about 6 to melt it and 46 kilojoules to boil it. Here's what's called a heating curve. And a heating curve, you will notice that there are several different pieces of this curve where we have plateaus where the temperature is remaining constant for some given amount of time. Wherever there's a plateau, that means a phase change is occurring. Energy is being used to break intermolecular forces instead of increasing the temperature. So you can put in energy and it can increase temperature, or it can break intermolecular forces. So we always want to see that these plateaus are indicating a phase change. Down here it's melting, and up here it is vaporizing or boiling. So if we wanted to know how much energy is required to convert 55 grams of ice from -6 degrees, so I'm going to go ahead and write a little diagram, -6, my negative got cut off, at 55 degrees, all the way to a liquid at 55 degrees is what that should say. So what I'm doing is I'm taking it solid, and then I'm going to get it to its melting point, which is 0 for ice. I'm going to melt it, and then I'm going to heat it up to 55 degrees. So there's kind of 3 processes taking place here. I've got to get the solid from -6 to 0. Then I actually have to melt it. And then I have to increase its temperature from 0 to 55. So this becomes 3 different problems. We will use specific heat, which is the Q equals CM delta T. This will be used whenever we're just changing the temperature of something rather than actually changing the state. So first I focus on the ice, and I need to get the ice from -6 to 0. So I'm going to use Q equals CM delta T. Here's my given specific heat. Here's my mass of my ice. And the change in temperature will be 6 degrees Celsius. So it's going to require 689.7 joules of energy just to get the solid up to 0 degrees. Now we actually need to break the intermolecular forces to make it melt. So number 2 here is a plateau. Anytime it's a plateau, I'm going to use either the fusion or vaporization. This time, since it's melting, I'm going to use fusion. So 55 grams of water, I'm going to convert to moles using molar mass. And then I'll use heat of fusion. For each mole, it's going to require 6.01 kilojoules. So it required 18.3 kilojoules of energy to melt it. And then lastly, I've got to heat that water from 0 to 55. So Q equals Cm delta T again, because all I'm doing is heating. I use the specific heat of water given the mass of water. It's changing by 55 degrees, and here are the joules required. Now I need to add these 3 together. You'll notice I have 2 of them in joules and 1 in kilojoules. So convert them all to the same. I chose kilojoules here. And oops, I didn't put in the final answer here. I will do that, but we're converting them each to kilojoules, getting their final answer here, and that'll be the total amount of energy used.